In this video, we're going to go over the equations and formulas that's associated with work, energy, and power. So let's say we have a block that's resting on a horizontal frictionless floor, and we apply a force causing the block to move by some displacement d. The work done on the box by the force is going to be equal to the force multiplied by the displacement of the block. So that's the first way in which you can calculate the work done by a force. Now here's another situation. Let's say if we pull the block using a tension force, but the block is moving in a horizontal direction, so the displacement vector is along the x-axis, and theta is the angle between the force and the displacement vectors. We can calculate the work done by this force using a variant of the dot product formula, which is FD cosine theta. So if you know the angle between the two vectors, all you need is the magnitude of the two vectors times cosine of the angle between them, and that'll give you the work done by that force. Now let's say if you have the force vector and the displacement vector, but you don't know the angle between them, but you know the components of those two vectors. Well, you can calculate the work done by that force by using the dot product formula. So it's the dot product of those two vectors, which is you're essentially multiplying the x components together along with the y components together. This will give you the work done in the x direction, and that'll give you the work done in the y direction. Since work is scalar, you can just add them together to get the total work done by that force. So that's how you can calculate the work done by a force. Now, work is also equal to the change in kinetic energy. The work done by the net force acting on an object is equal to the change in the kinetic energy of that object. This is known as the work energy theorem. Now, kinetic energy is 1/2 mv squared. So the net work is going to be the difference between the final and the initial kinetic energy, which will simplify to this formula. It's going to be 1/2 times the mass times the square of v final minus the square of v initial. And that'll give you the work done by the net force on an object. Now, the work done by conservative forces like gravity, the electric force, or the restoring force of a spring, this is equal to negative of the change of the potential energy of the object. Gravitational potential energy is equal to mgy. You can also see it this way, mgh as well. You can get the same result using both formulas. The elastic potential energy stored in the spring is 1/2 kx squared. So let's say if you want to find the work done by gravity, it's going to equal negative times the change in potential energy, which will be mg delta y, or y2 minus y1. The work done by the spring is going to be negative 1/2 k times x final squared minus x initial squared. So basically we're using these formulas. So the work done by a conservative force is negative of the change in the potential energy, and the work done by the net force acting on an object is equal to the change in the kinetic energy of that object. Now, when dealing with gases, whenever a gas expands, it can apply pressure against the piston, which can move, and it can do work. So the work done by a gas is negative times the pressure times the change in volume of that gas. So that's another way in which you can calculate the work done by a gas, or just in general. Now, power is work divided by time. It's important to understand the difference between energy and work. Energy is something that an object has. An object can have kinetic energy, it can have potential energy. Work is really a mechanism in which energy is transferred from one object to another. So if you think of energy as money, like how much money you have in your bank account, work would be like the transaction, the deposits and withdrawals, the transfer of money from one account to another. So work has to do with the transfer of energy, and that energy is transferred by the action of a force acting on an object. So whenever you hear work, think of the transfer of energy, whereas energy is something that an object possesses. And whenever an object has energy, it has the ability to do work, which means it has the ability to transfer that energy to something else. Now, power is the rate at which energy is transferred. It's work divided by time. Power tells you how fast energy is being transferred. Work, kinetic energy, potential energy, they're typically measured in units of joules. The standard unit of time is the second. The standard unit for power is the watt. So 1 watt represents 1 joule of energy being transferred every second. So if you have a 500 watt generator, that means it could transfer 500 joules of energy per second. Or it could transfer 5,000 joules of energy every 10 seconds. So that's the basic concept of power. Now you can also calculate work by multiplying power and time. You'll see other formulas that would say energy is equal to power multiplied by time. And just remember, work is just the change in energy. Now, going back to this equation, power is work over time. Work is force times displacement. And we know that velocity is displacement over time. So we can replace d over t with velocity. So we get power is force times velocity. Now, we know that work is the dot product of the force and the displacement vectors. Instantaneous power is also the dot product of the force and velocity vectors. If you simply multiply these two together, this will give you average force. If you multiply force by average velocity, you get average. I said average force, but I meant to say average power. This equation here will give you the instantaneous power if you have the force and velocity vectors. But just remember that power is force times velocity. Now we talked about watts. It's good to know that a kilowatt is 1,000 watts. And if you come across this unit, the horsepower, 1 horsepower is 746 watts. So those are some conversion factors that you want to be familiar with. Now sometimes you'll see things like kilowatts, and other times you'll see kilowatt hours. The kilowatt is a unit of power. Make sure you understand that. Watts, kilowatts, those are units of power. And remember, power is work over time, and it's also force times velocity. The kilowatt is not, the kilowatt hour is not the unit of power, but it is the unit of energy. So that's what you'll typically see in your electric bill, how many kilowatt hours you've used for the month. So kilowatt has to do with power, hours has to do with time. When you multiply power and time, you get work, or the change in energy, which is how much energy has been transferred over that time period. So power multiplied by time give you the work, or the change in energy. in joules or kilowatt hours. So kilowatt hours, joules, these are units of energy and not power. So make sure you understand the difference between the two.